recording. Okay, so this is our second example. So the first example was a symmetrical loading. This is an example where it's unsymmetrical loading. Again, apologies for the scribbles. I'm using the mouse to draw these things, and hopefully I'll have improved technology later in the week or next week. So what we want to find out is we want to find out that the capacity of this section in tension. So we have a section which is in unequal angle section. So its height is 150, its width is 75, and the thickness of the legs are 10 millimeters. Okay, so it's an unequal angle section, and that section has got loading in it applied to it through those bolts. Okay, so we have a load applied to it through the bolts, and what we want to do is we want to find out what the capacity is of the section. So similar to last time. Okay, so we have 3 bolts here, and 3 bolt holes, 1, 2, 3. The diameter of the bolt hole is 22 millimeters. The pitch between the bolts is 60 millimeters, so 60 millimeters between the 3 of them. The grade of the steel is S355 grade of steel, so that's an S standing for structural steel. 355. So 355 gives you an indication of what the yield strength of the material is. So if we have the thickness of the plates is less than 40 millimeters according to table 3.1 that we just looked at earlier on. Table 3.1 in Eurocode 3 part 1 part 1, the Fy is equal to 355 newtons per millimeter squared. Okay, so I suppose that will be the first thing that we write down for our solution, where we have the thickness in the member is equal to 10 millimeters, and that's less than or equal to 40 millimeters, and it's this grade of the steel S355. So then table 3.1. Okay, so that table 3.1 in Eurocode 3 part 1 part 3 or part 1 part 1 will tell us that Fy is equal to 355. Okay, so it's stronger steel than the last example. So the last example was S275, this is S355. So it's 355 newtons per millimeter squared. And the ultimate strength, in that table is equal to 510. Oh, that's my okay. Newtons per meter squared. Okay, so notice I could put 355 newtons onto any square millimeter, so a millimeter by millimeter piece of steel. If I put 355 newtons of a force on it, then that will get it to yield. If I exceed the 510 newtons for every millimeter of section I have, so if I went over to this edge here and I took a little millimeter by millimeter section over there, that section like that, if I put more than 510 newtons on that little bit there, that would cause would exceed the ultimate, and therefore it would break. We'd end up rupturing the section in there. Okay, so that's the first thing. The next thing, we need to get the cross section area in there. So we need to know what the gross cross section area is. So the gross cross section area. Gross. That's a G type. Gross cross section area. Okay, the gross cross section area A. Okay, so it's 150 high, it's 10 millimeters wide, so we can multiply 150 by 10 to get that area there, and then 75 minus the 10, so 65 here by 10 to get that area, and that would give us the overall area. However, it's a rolled section, there's actually a little fillet radius in here, so it gets a little bit thicker around the corner, and there's a little drop off on both ends there. So that wouldn't give us the exact area, but give us approximate area if we multiply by 150 by 10, and then we have 65 out here multiplied by 10. But there's a little fillet. Oh, sorry. Get the pointer going. Okay, so we could take the 150 high, multiply by the 10 wide, and that will give us a cross-sectional area of this bit. And then we take the 65, which is from here out to the end, and multiply by 10. That gives us the cross-sectional area there, and add two of them together. It was the overall cross-sectional area. But actually, there's a little fillet around the corner here, so there's a little bit extra area there, and there's a little drop-off of a fillet here, and one here as well. So it's a little radius here, a little drop-off here and here. So that wouldn't be exactly the cross-sectional area. So we go to the blue book, which is up on Blackboard, and I'll just show you that in a couple of minutes. But if I come off this screen, it disappears. I mean, I can't get it back, so I'll have to show you that afterwards. But just take it from me that when you go into the blue book, you can get the gross cross-sectional area, read it straight out of that book, and it'll tell you that it's 21.7 centimeters squared. And I'll show you where we get that now in a little bit. Okay. So that's the gross cross-sectional area. So then the plastic resistance from that then. So we know the plastic resistance. Oh, I do need to get it. Let's try this. So plastic resistance N P L R D is equal to the cross-section area. It's gross cross-section area times the yield strength, Fy. In this case, it's 355 newtons per millimeter squared, divided by gamma m naught, which is just equal to 1 in this case. Okay, so we have 21.7 centimeters squared, so I'm going to turn that into millimeters. So there's 10 millimeters in a centimeter, and it's squared, so 10 millimeters by 10 millimeters to get into centimeters. Is going to get us into by 100 to get into millimeters squared. Yeah, so there's 10 millimeters in a centimeter, and then we have centimeters squared. So millimeters squared will be 10 by 10 is 100. So I multiply 21.7 by 100 to get 2170. Sorry, 2170 millimeters squared. Okay, and the yield strength that we got from the code is 355 newtons per millimeter squared. Okay, so if we multiply those together, we can see that we have we're going to end up getting just newtons out of it, and the material factor of safety is just 1. Okay, so that's give us 770 by 10 to the power 3 newtons. And then just to neaten it up, and this is some feedback I gave to people, when you have newtons with such big numbers, it's easier to turn it into kilonewtons. So divide by 1,000 to turn it into kilonewtons. So 770 kilonewtons. Okay, so that's the plastic resistance. Now we want to look at near the connection here, over the connection in there. So we're going to get the ultimate resistance. So the ultimate resistance. So the ultimate resistance connection. We have 3 bolts. Okay, so we have 3 bolts. Okay, so that's going to give us. So that means that we're going to use the value which is beta 3 from the equation that I just showed you earlier on. A times the A net multiplied by the ultimate resistance, ultimate strength, sorry, of the material, divided by gamma m2. Okay, so we're using m2 because we're near the connection, and we're going to get that from equation 313, which I had up there a minute ago in Eurocode 3 part 1 part 8. Okay, so just take note of that there. That's Eurocode 3 part 1 part 8. So that's where we went to. That's free. Okay, so we have to work out what A net is. So what's the A net? So A net. So if we look at a cross section through, so looking at a cross section through here in there. So so I'm going to look at a cross section through here. We'll say back and over and on there. Okay, what's the net area from that cross section in there? So A net is going to be the overall cross section area, which was 2,110 millimeters squared, minus the number of holes. In this case, it's just one hole, times the bolt diameter, or sorry, the hole diameter, d naught, times the thickness of the section. So that's 2,170 millimeters squared, minus the number of holes, which is 1, times the hole diameter, which is 22 millimeters. It won't be 3, no, it's 1 because it's the, yeah, so n is equal to 1 because it's through the cross section. So if I take any section through this, so any section through this, so here I've drawn this yellow line here for this section through here, that's one section. I could take a section right the way in those holes, there'll be no hole there, then a section through here and so on. So it's a cross section. If I got a length, so think about your ruler again, if I got a saw and cut my ruler anywhere along the saw, or if I had this angle section here of length, say a meter, and I got a saw and I cut anywhere along through the section, okay, right across it to give me this kind of shape in there. So cut through here, there's only one hole as I cut through there. If I cut through here, it's one hole, and so on. I'd have to cut through longitudinally to get the 3 holes. So n is equal to 1. That's a very good question, because that's where loads of people make a mistake. They see 3 holes and they say, okay, n must be equal to 3, but it's through the cross section, and there's only one hole through any one cross section. Okay, so that's so n is 2, so that's the number of holes. 1 d naught is 22, and then the thickness of the plate material is 10 millimeters. Okay, so good. I have millimeters by millimeters, so that's millimeters squared. So that's 220 millimeters squared, and I have millimeters squared here. So I know I have the right units. So that's good, because I can't take away apples from oranges. They all have to be the same. So only apples from apples. So only millimeters squared away from millimeters squared. So that's equal to 1950 millimeter squared. Okay, so that's the net cross section area through here. This one here, or where the next hole is, and the next hole over there is, and so on in there. So next thing I need to work out is what the beta 3 value is. In the beta 3 value, as we discussed earlier, the beta 3 value comes from table 3.8 in Eurocode 3 part 1 part 8, and that's related to the relationship between P1, which is the pitch distance, and D naught, which is the diameter of the hole in there. So for beta 3, so to get beta 3, so we're going to have to look at what the pitch distance is. So P1, so we have to check to see what P1 is. So P1 is equal to 60 millimeters. So that's the distance between them. And we want to know what D naught is, so that we have D naught is equal to 22 millimeters. And then the value of P1 divided by D naught, so we put them over because we're looking to check this factor. If it's less than 2.5, then we have that beta 3 is equal to 0.5. So we have 60 millimeters divided by 22 millimeters. So it's always good to bring your units with you, because you can see then I have millimeters over millimeters, so they're going to cancel out. So 60 divided by 22 is 2.72. Okay, so in table, that table I showed you earlier on, so I can't go back and over between screens or it'll make this disappear. But so if I go to table 3.8, which is in Eurocode, so hopefully you have Eurocode 3, part 1, part 8 open up there in front of you. So if you go to that table in there, that will tell us in there that we have three bolts we have to interpolate because we're between 2.5 and 5. So it says that beta 3 is equal to 0.5 when P1 divided by D0 is less than or equal to 0.25, and beta 3. So this here, beta 3 is equal to 0.7 when P1 divided by D0 is greater than or equal to 5. Okay, so we're going to interpolate. So interpolate TE. Messy, so we're going to interpolate because we're at 2.72, so we've got 2.72, so we're greater than 2.5, we're less than 5, so we're in between those two in there. So we're going to have to interpolate between those two. Now let me see if I can get a new sheet here. No, I'll start again. Sorry, can't get a. Okay, so we're going to interpolate between those two. Okay, so we're going to interpolate between those two. So we have somewhere between 5 and 2.5. So we have. So what do we say again? I have to write it up here again. Sorry. So beta 3 is equal to 0.5 when P1 divided by D0 is equal, or sorry, is less than or equal to 2.5. And we have beta 3 is equal to 0.7 when P1 divided by D0 is greater than or equal to 5. Okay, so that's to interpolate. So, and we said we have so when P1 divided by D0, what we say we had is equal to 2.72. So that's a little bit higher than that. So the difference between these two, the difference between that and that is 2.5. Okay, so that's that one to that one is 2.5 between the two of those. The difference and that one is 0.2. Okay. The difference between this one and this one is 0.22. Okay, so it's 0.22. It's that proportion higher than 0.5, so we're 0.72 divided by the difference between this one and this one, so it's divided by 2.5. Multiply by the difference between 0.7 and 0.5, which is 0.2. Okay, so that's how much along we are on it, and then plus on to the 0.5. Okay, so we're just doing standard interpolation, so beta 3. Okay, so we know that the difference between this one, P1 over D 2.5, and that one is 2.5, but we're only 0.22 long, so we're only 0.22 bigger than 2.5. So 0.22 divided by 2.5, and then the difference in the betas between when it's at 5 is 7, when this factor here is at 2.5, it's 0.5. So the difference between those two, 7 minus 0.5 is 0.2. So multiply them up and then add on to 0.5. And then from that we get 0.52. So intuitively we should know that that's right, which is in, when we're at 2.5, the value is 0.5, we're only just above it, so we should only be just above a half. So we know if we've got our mathematical equation right or wrong. If we just kind of go, it looks around very close to 2.5, a lot further away than 5. So 2.72 is very close to 2.5, a lot further away to 5. So it'll be closer to 0.5 than 0.7. So 0.52 being the answer there. Okay, so then the ultimate resistance of that one is equal to beta 3. So this is from beta 3 that we just calculated, A net that we calculated on the page before, FU, which is the ultimate strength, divided by gamma M2. Okay, so if you remember for the symmetrically loaded section, beta, that beta value is 0.9. That takes into account the uncertainty associated with the ultimate. In this case, we're taking into account it's a lot lower than 0.9 because we have to take into account that moment that's been applied as a result of the axial load multiplied by the eccentricity. The net cross-section area that we worked out was it 1950 millimeters squared. And then the ultimate strength from table 3.1 is 510. 510 newtons per millimeter squared. And then the material factor of safety is 1.25 in there. Okay, so calculator to work this out. Normally I'll ask someone in the class to work it out. You can type it in if you can work it out faster than me. Calculator. Find the calculator. Okay, alright, so we'll trust Neve. 413712. Okay. 413, thanks Neve. 712. Newtons. Okay, and then divide that by 1,000 to get kilonewtons. So 413.7 kilonewtons. Okay, so that's the ultimate strength from there, and then the last line there. So in tensile resistance of that section is equal to the minimum value of the plastic resistance in PLRT, which we've already calculated on the previous page, times the ultimate resistance up times the ultimate resistance in U or D. So that's equal to the minimum. And so from the previous page we had 770 kilonewtons. And for this page, we have 413.7 kilonewtons. Okay, so it's the smallest because where is it going to fail? It's going to fail at wherever the lowest capacity is. In this case, the capacity away from the holes is 770 kilonewtons, whereas the capacity at the holes is 413.7. So that means that the ultimate resistance. So again, in the summations people made earlier, you didn't put down this last line. You just left, people to work it out. It's very important just to make it very clear what the answer is. At the bottom, no ambiguity. Basically, the design tensile resistance of the section is equal to 413.7, and if you put a nice red box around it, you can't miss it when I'm having a look or when somebody is checking it. That's the same in the design office. When I'm going back looking, I just have to go and pick the number at the bottom here. That's the design resistance in it, and I can compare that to what the load is, or the demand that I've worked out from my, say, truss analysis in there. So that's an example of an eccentrically loaded member in there. So has anyone any questions on that? No. Okay, so that completes the tensile design for now. So that's 2 examples in the tensile design. You've done one yourself as part of the assignment. When we go on to the project, we will be designing a truss members. So we design a number of different trusses that have compression members in them, tension members in them, and they will be eccentrically loading like this. So we will need to use this later on as part of our design project. So we're going to stop at that one now, and then we're going to move over onto the compression design. So just press stop recording here, and because I break them up, it's easier to break them up.